Hey there, welcome back. Ready for another deep dive?
You bet.
Today we're going to explore the fascinating world of metals and non-metals.
Yeah, the stuff that makes up.
Everything.
Exactly.
From the spoons we use to the buildings we live in.
To the air we breathe.
But we're going beyond the basics here, right? We're going to uncover those hidden properties and reactions that make these materials tick.
That's right. We're going to break down those differences between metals and non-metals and explore how scientists actually figure out, which is which.
And of course,
And how that plays out in the real world.
why does it even matter?
Yeah.
Okay, let's imagine for a second you're trying to cook an omelet.
Right.
Would you grab a rubber spatula to flip that omelet?
Probably not a good idea.
No, you reach for a metal one, but why is that?
Well, it all comes down to the unique properties of metals, you see.
Oh.
That metal spatula, it's shiny, right? That's what we call metallic luster.
Oh.
And metals also tend to be malleable, meaning you can shape them without breaking them, like hammering them into those thin sheets.
Oh.
Or ductile. You can stretch them into wires.
Oh, right, like the electrical wiring in my house.
Exactly. That's all thanks to the ductility of metals.
And let's not forget how quickly that metal spoon heats up in a hot soup.
Oh, yeah.
Conductivity.
Exactly. Metals are excellent conductors of both heat and electricity.
So that's why they're used in everything from cooking pots to electrical circuits.
Precisely.
Okay, this is all making sense now. But aren't there some exceptions to these rules? I vaguely remember something about a metal that's liquid at room temperature.
You're thinking of mercury.
Mercury.
It's the only metal that exists as a liquid at a typical room temperature.
Really?
And then there's gallium, a
Gallium.
metal that actually melts in your hand.
Wow, that's wild.
Pretty cool, huh?
Yeah, and what about on the flip side? Aren't there some non-metals that are surprisingly shiny?
You're right, there are always exceptions.
Even though we usually think of them as dull?
Yeah, iodine is a great example. It's a non-metal,
Okay.
but it can actually have a bit of a metallic sheen to it.
Huh. So appearance alone isn't always enough to tell us if something is a metal or a non-metal. What else do scientists look at?
Well, that's where chemical properties come in.
Okay.
You see how a substance reacts with other substances can tell us a lot about its nature. Let's take burning, for an example.
Okay.
When you burn a metal in air, it often forms a metal oxide.
Metal oxide.
Think of rust,
Huh.
which is iron oxide.
So rust is basically iron reacting with oxygen in the air.
Precisely.
Okay.
And many of these metal oxides, they dissolve in water to form solutions that feel slippery.
Interesting.
We call these solutions alkalis.
Alkalis.
Mhm.
Okay, so burning metals can create alkalis. What about non-metals? Do they react differently?
They do.
How so?
When nonmetals react with oxygen, they tend to form acidic oxides.
Okay.
And these oxides dissolve in water to form acidic solutions.
Acidic solution.
Yeah. Remember that lemon juice you used to clean tarnished copper?
Uh-huh.
That's an acid reacting with copper oxide.
So it's all about the oxides.
Yeah.
Metals forming basic oxides and non-metals forming acidic ones. That's a neat way to differentiate them.
Right.
But I have a feeling there's a lot more to these reactions, right? What happens when we throw water and acids into the mix?
You're on the right track.
Oh,
Some metals react vigorously with water, while others barely react at all. For instance, potassium and sodium are so reactive they need to be stored under oil to prevent them from exploding on contact with water.
Whoa, exploding metals. That's pretty intense.
Right. And then you have metals like gold and platinum, which don't react with water at all.
Huh. That's part of what makes them so valuable.
Exactly.
So how do scientists keep track of all these different reactions?
Well, they use something called the reactivity series.
The reactivity series.
It's basically a ranking of metals based on how easily they lose electrons and form positive ions.
So it's like a popularity contest for metals?
Huh.
The most reactive ones are the ones that are eager to give away their electrons.
That's a great way to think about it. And this reactivity series isn't just some theoretical list. It has real-world applications, particularly when it comes to extracting metals from the earth.
Okay.
But before we dive into that, let's take a step back and talk about what happens when metals and non-metals come together.
Okay, let's break it down. What's going on at the atomic level when these two types of elements interact?
At their core, metals have a tendency to lose electrons,
Okay.
becoming positively charged ions. Non-metals, on the other hand, prefer to gain electrons, becoming negatively charged ions.
Right.
And as you know, opposites attract.
So it's this attraction between positive and negative ions that leads to the formation of ionic compounds.
Exactly.
Like table salt, which is sodium chloride.
Precisely. Sodium, a metal, loses an electron to become a positive ion, while chlorine, a nonmetal, gains that electron to become a negative ion. They then attract each other, forming that crystal structure we know as table salt.
So these ionic compounds aren't just a random jumble of atoms.
No.
They're a highly organized structure of tightly packed ions.
Precisely. And this structure gives ionic compounds some interesting properties.
Like what?
For instance, they're usually solid at room temperature and have very high melting points.
That's because breaking those strong ionic bonds requires a lot of energy.
Exactly.
That explains why salt doesn't melt in a hot pan. So we've covered the basic properties of metals and nonmetals, their reactions and how they form ionic compounds.
We have.
But I'm curious about where we actually find these elements in nature. Are they just lying around waiting to be picked up?
Not quite. While some metals like gold can be found in their pure elemental form, most metals are found in what we call ores.
Ores, what are those exactly?
Ores are rock that contain a high enough concentration of a metal to make extraction economically viable.
Okay.
Essentially, they're rocks that are worth mining for their metal content.
That makes sense. So the reactivity series we talked about earlier probably plays a role in how we extract these metals from their ores.
You bet it does. The more reactive a metal is, the more difficult it is to extract from its ore. But before we get into the specifics of metal extraction, let's take a moment to test your understanding of what we've covered so far.
Sounds like a good plan. See if I've been paying attention.
All right, let's put your knowledge to the test.
Okay.
Can you tell me why a frying pan is typically made of metal while its handle is often made of plastic or wood?
That's a good one. Let me think. We know metals are excellent conductors of heat, so that explains the pan itself. We want that heat from the stove to transfer efficiently to our food, but we wouldn't want that heat traveling up the handle and burning our hand.
Right.
Exactly. That's why we use materials like plastic or wood for the handle.
Okay.
They're poor conductors of heat, so they act as insulators protecting our hands from the heat.
So it's all about choosing the right material for the job based on its properties. Precisely.
That makes perfect sense. Now I'm really curious to learn more about how we get those metals out of the ground in the first place.
It's a fascinating process, and as we discussed, that reactivity series plays a crucial role.
Okay.
For metals like gold, which are found in their native form, the extraction process can be as simple as physically separating the gold from the surrounding rock.
Oh, wow.
But for most metals, we need to employ more complex techniques.
Like what?
Well, let's start with those metals that are in the middle of the reactivity series.
Okay.
One common method is called roasting.
Roasting.
It involves heating the ore in the presence of air, which converts the metal sulfide to a metal oxide.
So we're essentially using oxygen to transform the ore into a form that's easier to work with.
Precisely. Another method is called calcination.
Calcination.
Which is similar to roasting, but involves heating the ore in the absence of air. This is often used to decompose carbonates, converting them into oxides.
Okay, so roasting and calcination help us get those middle-of-the-pack metals, but what about those highly reactive metals at the top of the reactivity series? You mentioned electrolysis earlier. Can you break that down for me?
Sure. Electrolysis is a powerful technique that uses electricity to drive a chemical reaction.
Okay.
In the case of metal extraction, we use it to force those reactive metal ions to gain electrons back, converting them into pure metal.
So we're basically using electricity to reverse their natural tendency to lose electrons.
Exactly. It's a bit like using a battery charger to replenish the electrons that those reactive metals are so eager to give away.
That's a great analogy. I'm starting to see how this reactivity series is like a roadmap for metallurgists, guiding them toward the most effective extraction methods.
It is.
But even after all this effort to extract these valuable metals, there's still that constant threat of corrosion, isn't there?
Unfortunately, yes, corrosion is a natural process that can't be completely eliminated.
Right.
But we can certainly slow it down and protect those metals. We already talked about how some metals, like gold and platinum, are naturally resistant to corrosion.
Yeah.
But for metals like iron, which are prone to rusting, we need to get a bit more creative.
So what are some of the tricks of the trade when it comes to preventing or minimizing corrosion?
One common technique is galvanization.
Galvanization.
It involves coating iron or steel with a thin layer of zinc.
Why zinc? Does it have some special anti-rust properties?
Zinc actually has a higher tendency to oxidize than iron.
Uh-huh.
So if the zinc coating gets scratched, it will corrode, preferentially sacrificing itself to protect the iron underneath.
That's pretty selfless of zinc. So it's like a protective shield that takes the hit for the iron. Pretty cool. And speaking of combining metals, let's circle back to alloys. I know they're mixtures of metals,
Yeah.
but I'm curious about what makes them so special. Why not just use pure metals for everything?
That's a great question. Alloys are all about enhancing the properties of metals to make them even more useful. Think of steel, for example. It's an alloy of iron and carbon.
Right, steel is much stronger than pure iron, but why is that?
The addition of carbon to iron changes its crystal structure, making it more resistant to deformation.
Okay.
That's why steel is used in everything from bridges and buildings to cars and tools.
So by adding a small amount of another element, we can drastically change the properties of a metal. What are some other examples of alloys and their unique characteristics?
Well, brass, an alloy of copper and zinc, is known for its durability and golden color. It's used in musical instruments, plumbing fixtures, and even decorative items.
Okay.
Then there's bronze, an alloy of copper and tin, prized for its hardness and resistance to corrosion. It's been used for centuries in sculptures, bells, and even weapons.
It's amazing how these different combinations of metals can create such a wide variety of materials. But before we get too carried away with the metallic world, let's give some attention to the non-metals.
Yeah,
They're just as important, even if they don't always have the same flashy appeal as metals.
you're absolutely right. Non-metals are essential to life as we know it. Think about the oxygen we breathe, the carbon in our DNA, and the nitrogen in the air. They're all non-metals.
It's easy to take those for granted because they're all around us.
Yeah.
But let's talk about their chemical behavior. We mentioned earlier that they tend to form acidic oxides in contrast to the basic oxides formed by metals.
Right.
Can you give me an example of that in action?
Sure. Sulfur dioxide, a non-metal oxide, is released when fossil fuels are burned. It reacts with water in the atmosphere to form sulfuric acid, which is a major component of acid rain.
So that's the connection.
Mm.
Acid rain is caused by those acidic oxides reacting with water, but nonmetals can also react with hydrogen. Right, you mentioned hydrides earlier. What are those like?
Hydrides are compounds formed when hydrogen combines with another element.
Okay.
They can be quite diverse in their properties. For example, ammonia, a compound of nitrogen, and hydrogen is a common household cleaner.
So we've got acidic oxides and hydrides, quite a range of chemical behavior for those nonmetals. But do they react with acids in the same way that metals do?
That's a great question, and the answer is no. Remember how metals react with acids to produce hydrogen gas?
Yes.
Well, nonmetals generally don't displace hydrogen from acids. They have their own unique reactivity patterns.
Okay, so they're definitely not just mini-metals. They have their own distinct chemical personalities. But we focus so much on chemical properties. Are there any interesting physical properties of nonmetals that stand out?
Well, we know that nonmetals are generally not as shiny or conductive as metals.
Right.
But as with everything in chemistry, there are exceptions. We already talked about graphite, a form of carbon, being an excellent conductor of electricity.
Right. Graphite, the nonmetal that can conduct electricity. It's always good to be reminded that there are exceptions to every rule.
Yeah.
Any other surprising nonmetals?
How about the hardest naturally occurring substance known to humankind?
Ooh, that's got to be a metal, right?
No, it's diamond. Another form of carbon. Not only is it incredibly hard, but it's also an excellent thermal conductor.
Wow. I would have never guessed that. So even within the realm of nonmetals, there's a surprising amount of diversity.
Absolutely, and that's what makes chemistry so fascinating.
Well, I think we've done a pretty good job of exploring the key characteristics of both metals and nonmetals.
We have.
We've covered their physical and chemical properties, their reactions, and even how they're extracted and used in the real world.
Indeed, we've seen how their unique properties determine their applications, from the metals in our smartphones to the nonmetals in our bodies.
This has been an incredibly insightful deep dive. But before we wrap things up, let's pose a challenge to our listeners. Think about all the materials you encounter in a typical day.
Ooh, I like where this is going.
From the metal in your smartphone, to the plastic in your water bottle, the glass in your windows, to the concrete in our sidewalks. How does our understanding of metals and nonmetals shape the design and creation of these everyday materials?
That's a fantastic question to leave our listeners pondering. It really highlights how deeply intertwined chemistry is with our everyday lives.
It really does.
But before we sign off, let's recap some of the key takeaways from our deep dive.
Sounds like a plan.
Yeah,
We've covered a lot of ground, so a quick summary is definitely in order.
for sure.
First and foremost, we established that metals and nonmetals have very different properties and behaviors.
Oh.
Metals with their shiny luster, malleability, ductility, and excellent conductivity tend to lose electrons and form positive ions. Nonmetals, on the other hand, are generally not as shiny, tend to be brittle, and are poor conductors. They prefer to gain electrons, forming negative ions.
Right, and those contrasting tendencies are what lead to the formation of ionic compounds, where those oppositely charged ions, positive metal ions, and negative nonmetal ions are held together by strong electrostatic forces.
And these ionic compounds, like table salt, have high melting points and conduct electricity when dissolved in water.
Exactly.
We also dug into the world of extracting metals from their ores. We saw how that reactivity series we talked about plays a key role in determining the best method for getting those metals out. Low reactivity metals like golds are sometimes found in their pure form, which is pretty cool.
Yeah.
But those higher up in the reactivity series, the ones that love to give away their electrons, require more complex techniques like roasting calcination or even zapping them with electricity through electrolysis.
And of course, we couldn't forget about corrosion, that pesky process where metals react with their environment and start to deteriorate. We learned about some clever ways to combat corrosion from protective coatings like galvanization, where zinc heroically sacrifices itself to protect iron, to the amazing world of alloys where we mix and match metals to create materials with enhanced properties.
Speaking of alloys, those were a real highlight for me. Who knew that by combining metals, or sometimes even a metal with a non-metal, you could create materials with such a wide range of properties tailored to specific applications? Steel, brass, bronze, and even those super strong alloys used in jet engines are all testaments to the power of alloying.
And let's not forget about those unsung heroes, the nonmetals. We saw how crucial they are to life itself, from the oxygen we breathe to the carbon that forms the backbone of all organic molecules. And despite their reputation for being a bit dull, we saw that they actually have a diverse range of chemical behaviors forming acidic oxides, hydrides, and even some surprises like graphite and diamonds.
It's amazing to think about the sheer variety of materials that exist in the world, and it all boils down to the fundamental properties and interactions of these basic building blocks, metals and nonmetals.
Well said. Our deep dive has taken us from the atomic level to the everyday objects we use, showcasing how chemistry shapes the world around us.
So the next time you pick up a metal spoon, turn on a light switch, or simply take a breath, remember the fascinating world of metals and nonmetals that makes it all possible.
And on that note, it's time for us to say goodbye. Keep those curious minds engaged and join us next time for another deep dive into the wonders of science.